Welcome to Lecture 11 and 12, which is going to look at operating systems, particularly an overview of operating systems, then its component parts, and maybe what it actually does, the processes it undertakes. So this is for course Comp 19512, Introduction to Computer Systems. So over the next few weeks, or a bit longer than that, the university will ask you to fill in a form-based, web-based questionnaire for this course, so if you'd be so kind to fill that in, that would be very kind of you. So now moving on to Q3s from last week's lecture. So last week's lecture was looking at hierarchies, in fact explicitly memory hierarchies, and the fact was that the CPU was at the top of this hierarchy, and then below that was the primary memory, M1 if you remember, with access time T1, then below that was M2, the secondary memory with access time T2. So let's look at some questions relating to last lecture we undertook. The first one was this concept of hit rate. So let's interrogate the first question. So Q1 and Q3 is, what is the basic equation for the hit rate? I'll leave you a few seconds to think about that. So the hit rate is the number of accesses serviced by M1 divided by the total number of memory accesses. So the total number of memory accesses serviced by M1 and serviced by M2 added together. So now if we move on and use this hit rate H, so here's the hit rate in a percentage figure, 80%. What can we do with that? Well, one of the things we can do with the hit rate and the access times for T1 and T2 is calculate the average access time. So let's read out the question now then. If the hit rate is equal to 80%, what is the average access time? And then we're given the two accesses time for the primary and secondary memory, M1 and M2, which is the times are T1 50 nanoseconds, 10 to the minus 9, and T2 5 milliseconds, 10 to the minus 3. So I'll give you a minute to think about that. So the equation we need to use is T subscript AV equals T1 plus T2 times 1 minus H. So if we substitute in 50 nanoseconds for T1 and 5 milliseconds for T2 and then times it by 1 minus H, remembering H here is interpreted as 80%. So then we've got this sub-bracketed component to work out first. So it's 1 minus 0.8 is 0.2, so it's 0.2 times 5 times 10 to the minus 3 gives us this value here of 0.1 times 10 to the minus 3. So then we accumulate these two, add these two together, 50 nanoseconds and 0.1 milliseconds. We get this figure here of 0.000100005. If we change that to SI units, which are reasonable, that's 100.05 microseconds, 10 to the minus 6. Then we looked at hard disks. So a question relating to hard disks is, question 3 is, what is the latency of a hard disk related to? I'll give you a few minutes to think about this. So the latency is related to the rotation speed of the disk. The latency is actually the time it takes to find a sector on a track when the sector is, well, you first move to the right track, which is maybe halfway across the disk, and then you move round the disk to the right sector. So the latency is important, and it's related, as it says here, to the rotation speed. Now what we're going to do is remind you about feedback. So at the end of the course, after the 3 weeks Easter holiday, you can get some feedback which might be very useful to you. So there'll be a number of, in fact there'll be 2 feedback sessions in my office in G12. Now here's the process to go through that I went through last time. So really you've got to go onto Blackboard, click the appropriate icon, which is feedback booking process. Will tell you how to do it, which will be these steps, and then click this icon, which is the coursework feedback times, and that will then give you this table so you can allocate yourself or select a time you prefer for feedback. And as I've said, the type of feedback I mentioned last time. Now what we're going to look at is this concept of operating systems. So operating systems themselves are placed on top of the hardware. They control the hardware. So we're going to look at it, overview it first, and then look at the sub-components in it, and then what it actually does, the processes. So we'll have a quick introduction, then we'll have a break where you can actually talk about coursework if you need me to review any of it before you hand it in. So the first thing we're going to look at then is the major components in the operating system, and we're going to explain their function and identify them. So let's move on to those then. So an operating system then is software that sits in the computer. It's used by the computer, and the sort of things it's used to do, well, let's have a look at them now. Well, the first thing it does is the operating system actually controls the computer. So it's actually controlling the computer, and the user might be manipulating the computer via the operating system. So as it says here, it provides a means of undertaking that process of control using the operating system and controlling the computer itself. So the second thing it does is it provides us the ability to store files, store programs, and that can be seen as a way of managing resources, which are files and programs and data, because the data is going to be processed maybe by the program, so it can manage resources on the computer. These resources may be, as we've seen before, on the secondary memory. So the next thing that's important is this managing is really sorting out a hierarchy, a topology, or an organization of files. So that's what it's actually able to do by managing these resources. It organizes them into directories, and the directories may have a number of files in them. So the next thing is this concept where we've got this idea of a memory hierarchy, but in fact that's slightly wrong, because the memory hierarchy is a bus structure. In fact, everything's connected to the bus, not just the memory. So these I/O devices, which might be things like USB devices or other devices like device drivers for printers and other things like that, also have to be controlled. So the operating system does that as well, and it does this via the particular I/O devices for a particular hardware device outside the computer. So what it's really doing is it's enabling the computer to run a number of programs at the same time. So that's what the operating system does. So now we're going to look at a very introductory view of a personal computer, an end-user computer, and say, what are the typical types of operating systems for an end-user computer? And you'll probably know these. One of them is Windows. Its variety at the moment is Windows 7. It's gone through a number of varieties, from XP to Vista to, before that, quite a few others. And then another variety of software operating system is Unix, which has different types of implementations. One of those is Linux. But there's also many more different types of operating systems, which are nominally used on embedded systems, which might be specifically designed to do jobs like lifts, like subsea control systems, like car management systems. All of these, particularly the ones running to control systems that are running in real time, will require real-time operations. Particular examples of those are VRTX, which is a small operating system that runs on embedded systems, or a larger one is OS 9. Both of those two I've just mentioned are totally different to Microsoft and Unix. Microsoft Windows and Unix are not real-time systems, or real-time operating systems to be explicit. So let's have a look at the historics view of this, and where did this terminology of operator come from, or operating system, and what does it do? Well, it allows different users the ability to run programs. And that's a pretty basic functional requirement of an operating system. But in the early days, the operating system, well, there really wasn't one, and there was just an operator, a human operator, who functioned as a human operating system. So what did this human operator do? Well, in the early days, programs were encoded onto cards and tape, and the human operator would put those into the machine, place them into tape readers, place them into card readers. So these programs, these set of punch cards, this serial set or stream of tape, these were actually called, and naming convention wise, they were called jobs. So the human operator placed a particular job, maybe it had a job number, into the machine and ran it. So this was called submitting a job, which was a program to run on a big computer. So what did the operator do, which became the operating system? Well, the human operator first had to decide which job ran next. So he had to schedule it, or decide which to put in the machine to run. So that was the first thing he had to do. The next thing is, the operator may have had to set up the computer. So maybe put the cards into the card reader, then set the computer going, and afterwards it would gather, the human computer operator rather, would gather the results from a particular other location in the machine. So finally, the important thing to realize is it was the human operator who was responsible for this task of actually scheduling these items called jobs, which were programs, and managing their execution, putting them into the machine, and then extracting the results when they were actually finished processing these jobs. So really this idea of running programs was undertaken historically by human operators, if you like, a human operating system, which was a human undertaking the task that a modern day operating system does. But they only probably would run one program at a time through the computer. So we'll have a break now, and then if you want, in the real lecture we can have a talk about coursework. So moving on from there then, now we're going to look at the second component of the course, look in a bit more detail at operating systems, so it's called Operating Systems 2. Again, we're going to look at an overview of the operating system in a bit more detail. We'll introduce a diagram and introduce the concept of layered operating system. Then we'll look at its components, so we go into the bottom layer and start naming the components, and then the processes that these components enable the operating system to, the functions they enable you to undertake for the upper software, if you like, above the operating system. So let's look at the learning outcomes for this lecture. The first thing to realize, by the end of the lecture we should be able to explain what this technical term of batch processing is. So we'll see what that is in a moment. Then we'll understand this concept. Well, we've looked at uniprogram or single user. What about multi-user programs? So maybe we then move on to a different concept of multitasking. We also have already introduced this concept of a job, which we're going to link to this batch in a minute. So the next thing we're going to move on to is we look into the operating system, name the two layers in it, and then look at the bottom layer, give that particular name, and look at the major components in it. And then we explain in a bit more detail what each component or functional block actually does. Then we see how we load the operating system, and this naming convention for loading the operating system is called Bootstrap program. It's a particular program that does a particular task. It's quite interesting how it does it, because it moves between different memories, so we'll see how it does that in a minute. So moving on then, we've got a lot of comprehension to do. The first thing is, previous set of slides introduced this concept of a job, a single program. And if we have a number of these with different job numbers, job 1, 2 and 3, they'll run sequentially, as it says in the notes, one after the other. So if we put these together in a set, this set of jobs is called a batch. So a batch is a collection of jobs. Now when we've generated these jobs and formed them into a batch, we can then run them at any stage. So we can just use that batch and put them into the computer. And then if we want, we can use those results from the initial batch in a later batch. This is even used to this day actually, and they're called batch processing. So it was developed as a term. You can actually run batches, and if you go back down to the DOS command, the control window in Windows and even in Unix, you've got this file that you can run which will run a batch of commands or a program, and it has a suffix .bat for a batch program. So they're still using the terminology even today. So what does a batch process have as the sequence it performs? Well, there's 3 steps nominally. So first, the operator, the human operator, gathers together a set of programs. So the set of jobs, probably numbers them job 1 to 3 or something like that. And then this becomes the batch. this batch in step 2 is submitted to the computer, and then finally after that the jobs are run. The programs are the jobs themselves, and they're run in order sequentially. When the jobs are complete, there's an output which the operator again will collect or reuse for the next batch as data into the next batch program. The important thing to realize here is that the human operator, the operating system if you like, sudo maybe, is and has no intervention at all with the program while it's running through the program. So while it's batch processing, sequencing through the jobs 1, 2, 3, jobs 1, 2 and 3, nothing will be done by the human operator unless there's an error. If there is an error, the operator will have to come in and deal with it. So, well, if you thought this was old terminology, no, it's still used for major operations. One of them is payrolls. So that means if there's a number of files that have to be run through, a number of common operations that have to be done on a number of files, and that's exactly what happens in a payroll, have to pay a certain amount of tax, have to pay a certain amount to particular employees, that's the sort of job that even now is done, common operations on different common files. This is a batch processing task, which is payroll systems, who will pay through this batch processing particular amount of tax to the tax man, and also calculate how much pay each person will get, print out a form and then submit the amount to particular bank accounts. So batch processing now is done, and also you might also have modern multitasking systems that can use this type of approach. So let's look at a diagrammatic depiction of batch processing then. The first thing to realize is the human operator will create the batch out of a number of jobs, and here we've got 5, job 1 to 5. They're normally put in a sequential queue. This is terminologically speaking called a first in first out queue. That means this job is the first in and this is the last. This will be the first out of the queue. The queue then, and the either card reader or tape reader, will then read these jobs, execute the programs and output the batch results. And it'll do that in an ordered way, and it'll execute them orderly one after the other as a batch process. Now let's think about this, because batches, as we've said, don't allow any interaction while the batch is running on the machine. So it doesn't allow a user to do anything, input data, modify things. So it's important to realize if we need to do something called, in a naming convention for it, is interactive processing, the user needs to interact with the jobs while they're running. So that's what we might need to do. So let's have a look at some examples of this. One of the ways of interactive processing that needs control of a program as it executes. And examples of these, as you would gather, are word processing. That's a typical example of this. Now we move on to time sharing as a naming convention we're going to introduce, and the associated concept of multitasking. So let's first say that we've already introduced this concept of interactive processing. So we've introduced it and said it's quite straightforward. It means there's one user interacting with a computer, maybe only one program executing at a given time, and that's what he's doing, but he might be adding data to that program while it's running. So, but what if the program is interacting with the user all the time? So what does this mean? Well, the important thing to understand here is that this historically is quite time consuming. It might be more necessary for a user, and one of the important things is there might be, initially before we go to the systems we've got now, many users using one system. So historically computers were undertaking a number of tasks. So if we're looking at this concept of time sharing and multitasking, the first thing we have to introduce that maybe a computer, when it's more widely used, needs many users to be supported at once. So how would that be done for different programs? So let's move into introducing these concepts a bit more in detail on the next few pages. The first thing to realize is this is what a multi-user system may look like diagrammatically. Well, there used to be one computer with many users. We still do this with our Unix system, where we log in sometimes to a particular Unix host or server and then have many users. So this is still done even to this day, have multi-user systems. Now the next thing to realize is our next naming convention for multi-user systems is that the multi-users have to share the CPU time, and this is normally called time sharing, and it's a time sharing scheme to, if you like, let one process or program run on the CPU and then another. So we'll look into how that's done now. So the important thing here is that the processor, even though it might appear to be, can only execute one program or one process at a time. So the little man computer can't do this. It can only basically run one instruction at a time. So it can't do this clever thing of multitasking. But if we do have many users, we need to be able to do this, to respond to a user's interaction, and for the user to think, well, there's no time delay and I can't see any difference. It looks like I have total control of the machine. So it might be one user word processing, and it might feel or look and feel as if there's no delay, but there might be behind the scenes. So the concept we're talking about is that the system itself, or the computer, is actually time sharing the resources. So what does that mean? It means for each user, for a short period of time, their program is running on the CPU. So it'll be executing, and then for another period of time we're going to swap to another user's program. So let's have a look at the next slide and see if we can diagrammatically depict this and give a few more naming conventions, exact terminology, academic terminology or scientific terminology for what's happening here. So here's a diagram depicting multiple users. We're going to call them user 1, user 2 and user 3. And each user, when they have the machine, will be given this idea or concept of using the resources by this green square. When we swap between users, we're going to give it a particular name and change the colour of the operation to this colour here, which is brown. Now we're going to explain what happens in real time when we switch from user 1 to user 2. Now before we do the switch, I'll just explain. User 1 will be fully using the CPU. The program will be incrementing through the program one instruction at a time. Now if you remember back to the little man used the program counter. So in fact what will be happening is it'll run one instruction, then it'll go and look at the next instruction pointed to by the program counter. Now when we do this next operation, which is called switching, explicitly context switching, we stop the processor. We save the program, we save the value of the program counter, we save any registers, we save them down, and then we swap over to the next program. So context switching, the word context means we switch contexts of program. So the context that's running on the first user's program will be all the registers, if they're being used by the program, will be in use by that program and need to be saved. One particular program register we need to save is the program counter that points to the next instruction. So they're all saved down. Now we move to user 2's program, where the context is changed to that program. So we load in that program. Now if it was running before, we'll have saved down all the information. We'll load up its program counter, any registers it was using and any data, and then we've context switched to the next user's program. And we do this again, so we now switch to user 2's program. So we save user 3's program we're going to switch to from user 2. So we save user 2's all the metadata, the registers that was using the program counter, save them down, and then we load into the computer, the processor, the next programs, user 3's program, their program counter, their metadata registers, and then we run it, let that program step through the instructions and use the CPU time. So that's what it basically is. So context switching is uploading and saving down the previous program to upload the next data from a back-end store, like the secondary memory. Let's move on now. So we've talked about time sharing, and we could do this on a single user computer, and that could be called a personal computer, and we do this maybe all the time with a single user. So it's slightly different now. We haven't got multiple users, but instead of users we have many different processes. They sometimes are called threads because a process can run in a thread, and can run at the same time, these processes. So let's have a look at this. So some of the processes that might be running in real time might be, and together, virus checker, and you might be word processing at the time, and in the background before you went back to word processing you're downloading a file, and you're also listening to an MP3 file. So what is this called? So this is called time sharing. In this type of system where there's a single user, it's called multitasking. So multitasking is this idea of switching between different tasks and time sharing the CPU. Modern operating systems like Unix, Linux and Windows actually do this. So this means that single programs that are running on computers are actually running at the same time as other processes or programs on the same machine. So let's have a look at that in the next diagram. So here we can see via the Windows Task Manager window, we can see that at the same time when this snapshot was taken, actually quite a few tasks are running. Okay, so you can see different types of tasks are running at the same time. Now, this diagram is maybe quite important because it visualizes the layers of an operating system. So simplistically, the operating system with respect to the user has two layers. And also with respect to any application programming using the operating system, it goes through a different entry system to a human user. The application program like Excel or MS Word will go through an application program interface, an API. There's a lot of APIs, and the API is an interface, a layer above the actual bottom layer of the operating system, and that naming convention used for that is the kernel. So let's go back to the top level layer for the user. This is called a shell, which protects the kernel from users, and it has a particular manager in there which will manage interaction between the user and the bottom level kernel. And the application program goes through its API interface and can also get operations to run particular functions. So now let's look at this lower level kernel. It has a number of functional blocks we're going to talk about. It probably has more than this, but we're only going to focus on 5. The first one we're going to talk about is Memory Manager. Now that has the job of doing something like, well, there's a program in the back-end store, the secondary memory, the hard disk. It's a large program. We can't run all of it, and we might have to use another part of the kernel to actually obtain it. So let's just talk about and come back to the memory manager, the file manager. So the file manager will let us interact with this hard disk, this secondary memory, and find the location of the program. So once we've used the file manager to read or write the data, in fact, let's just say we're reading it, we go back to this memory manager, which will take this big program and maybe take a small portion of it because it can't all fit into the main memory, and then it'll take that chunk and place it in memory. So that's what the memory manager basically does. Now we can move on nicely to the scheduler and dispatcher. Once we have a program in main memory, which has been handled by initially the file manager in the operating system, and then the memory manager is taken over from the file manager and even use the file manager functionality to get a block of the main program and move it into the primary memory, then the scheduler can actually schedule which one of these programs, because there might be lots of blocks in main memory which are parts of programs, and it will schedule them in order and then dispatch them, the particular one that's going to run, to the CPU, the processor, and run it. So let's look at some other functions that performs. Well, one of them is there's actually lots of devices connected to the bus. The initial view I gave you of the memory hierarchy made up of a processor, followed by the main memory M1 and the secondary memory M2, is a little bit fuzzy. That's what it is like, but actually everything's connected to that bus that the memory is connected to. So all of these devices, USBs, networks, all of these printers, everything's connected via device drivers. So there'll be a lot of device drivers that have to be either preloaded with the operating system or loaded when the device is first connected to the machine, like a USB driver. Now if we're going and interacting with the internet is connected via lots of subnets. These subnets talk a particular language, have particular rules called protocols. This network manager functionality will enable the operating system to perform that interaction between this computer and any subnets that connect to the internet. Let's move on then. So really let's reappraise those 5 functions. So the operating system really has many more important functions. We're only going to look at a subset of them, 5. So let's reevaluate what they were. Again, starting with the file manager allows us to put a topology, a mapping, a structure onto that hard disk to allocate locations, structures. So the file manager will manage the files on disk and lay them out in a particular format, in a directory structure. What else does it do? Well, we have this idea that lots of things can connect to the bus, and lots of other input and output devices need to do that, so we need this other functionality called device drivers, and sometimes you'll see them actually being loaded in real time, and you can see this particularly when you plug in a USB device. You'll see it loading the device drivers dynamically. So now the next thing that maybe works in association with the file manager functionality is this idea of moving a program or data into main memory, M1. That has to be done in smaller blocks called pages or segments in second year courses. So the memory manager looks after the RAM, looks after the main memory, and swaps in and out blocks of information, blocks of programs, and blocks of data. So that's what the memory manager does. So the next thing is, which one of these blocks of data in the memory is run by the CPU? Well, that's done by the function of the scheduler and dispatcher. What it actually does, it'll form a scheduler queue of programs which will be run on the processor, and then it dispatches them one at a time to the processor, and then it ensures the correct resources are used at the correct time. Now finally, if you want to interact to broader systems to get data to the internet and to the subnets involved in the internet, you need some form of functionality to support that. And this is done by controlling the network, which, as I said, had a number of rules, a number of functionality, a number of sequential processes it had to go through to send the data, break it down into sub-blocks and that sort of thing. This is done in the operating system by the network manager. Now the next thing we've got to look at, well, how do we get this all up and running? How do we get the operating system up and running? Remembering that most operating systems are actually stored on the hard disk, so they can't be run when the machine is powered up. How is it done then? Well, as they're so large and complex, they have to actually be loaded from the hard disk. So we need a loader to do that, and the form of memory that stores them, the loader that is called a ROM, which is a read-only memory, which is non-volatile, which will store, it's normally in a PC called a basic input-output system, so it's their BIOS. That BIOS is actually a loader which will then load the appropriate operating system into main memory. Okay, let's look at that in a bit more detail then. So the naming convention for this loader in the ROM is called bootstrap. So it bootstraps the program. What it actually does is the computer turns on. The ROM is powered up. So say that ROM has a memory mapped address of 0. It starts at the first address in the ROM, and then the ROM will go through instructions which will then go to the hard disk and boot the operating system. What it will actually do is it will load the relevant portions of the operating system from the hard disk, the file system, into main memory, and then it will run them. And again, you can see that it's used the file manager, the memory manager, and then the scheduler and dispatcher functionality to do that. But it's the ROM that actually loads in the operating system or portions of it to run the system first. So then it basically, once it's done that, hands over the driving of the hardware to the operating system, which will be run from the first instruction in the operating system, and it takes over control of the system. You can also have multiple boots. The one at home I have is dual booting between Vista and Windows 7. Another machine I have is booting between Linux and NT, I think. So there's multiple ways of booting and a number of ways to configure machines to multiple bootstrap from a ROM. So if you look and scan read these lecture notes again, if you find any difficulties, write the questions down for me. Now what I'm going to do is give you a mind map summary. So if you remember when we first started this lecture, we talked about a different type of processing. A type of processing where there were no operating systems, but synonymous to operator, there was a human operator. So the human operator put together a number of jobs. So each program was given a job number, job 1, maybe to job 5. This was called batch processing. These were either a set of cards or tapes. The operator loaded them onto the machine in a sequence called a batch, and then executed them, and the batch results are then returned and even reused in a subsequent batch. So that is even done today. Batch processing is actually done for payrolls. Now we started looking at the operating system in a bit more detail. We started naming the layers. So the upper level layer for the users is called the shell. The lower level layer below that is called the kernel. In that kernel, the 5 functions or operational blocks that we chose to look at were these 5 components. One of them was a file manager. So that looked after the files on hard disk, enabled it to format it, to configure it as a directory structure, and all those sort of operations. It stored addresses, and that's what it did. The next thing is device drivers. So there's a lot of other I/O devices on the system bus that the memory is connected to. So these device drivers have lots of I/O connections and lots of different I/O drivers. Then we move over to the memory manager, which might work in tandem with this file manager. The memory manager takes a big program and data maybe in the secondary memory, M2, and takes a block of the program and moves it into RAM, primary memory, because the RAM isn't as big as the main memory, so it'll take a chunk. These chunks are actually called pages or segments. So that's the memory manager that does that. Then the scheduler will actually schedule which one of these manager blocks programs will run, and then it dispatches that program to the CPU. Now if we use outside data, we might need to connect to a network, and it's the network manager functionality in the kernel that provides these tools to change the way the data is formed from parallel type of data, maybe as you view in a word processor, to serial data and bitstream it across a subnet. Then we looked at the concept of this idea of multi-user programs, and these were called multi-user in the context that they switched between users, and there was a particular name given to the time when they switched. And this naming convention came directly from the fact that program 1 had a context, and that was it was contextually processing the data it had at that instant, might have a set of registers and a program counter that shows where it was in the program. That was its context. So we switch context. We save those variables and registers and program counter, and when we do that, we context switch, load the next program's user 2's programs, and put those registers in and that program counter into the processor, and then let that segment of code run. So if you've got any questions, please ask me them in the lecture, and then we've got Q3s for next week. That's the end of this lecture.